So it's great to have George here with us. So George got his PhD from the University of Illinois, Urbana-Champaign with Charles Gami. He is a member of the EHT and lead the theory working group. So, and in addition to theoretical work, he recently built a radio interferometry at the IAS. So people know IAS is theoretical. So my prediction is both Leah and George will become John von Neumann, that they will be in the history of IAS, that they build actual stuff there. Okay, so I guess, George, your talk will be the next generation of horizon scale black hole accretion. So please take it away.
Thank you very much, CK. I'm really excited to have the opportunity to tell you a little bit about what I'm thinking about, the kind of science I do, and kind of my excitement over what I think the next 10 years, let's say, will bring in terms of horizon scale, low luminosity, black hole accretion science, as CK said. Also, since you brought it up, I figured I would say, so, right, so as CK said, we had this kind of EHT subgroup meeting at the IAS and thought it would be an interesting idea to try and build a radio interferometer as just kind of a cutesy thing for the meeting. And so we built two like 1.2 meter dishes and connected them and set them up. And there was like a surprising, this is being recorded, okay? Yeah. There were like a surprising number of people who came by and were like, are you supposed to be doing this here? This is supposed to be a place where people don't build things. And, you know, connecting to von Neumann. So when John von Neumann was doing his computing stuff, the lore is that they forced him to build all of his computing stuff off of campus. And so now the nursery school at the IAS is where all of his computers used to be. Anyway, as CK said, I am a theoretical and computational astrophysicist. I co-lead the theory working group. Yeah, so I'll tell you a little about what I'm thinking. I will stand, but be here because I have to control my computer. Okay, so brief outline for the talk. It's kind of a talk in 3 parts. I'll provide some motivation for why I think these problems are interesting. Tell you a little bit about my algorithmic approaches to solving or to thinking about these problems. I'll remind you kind of some of the state of the art of inference in terms of Event Horizon Telescope, observables, let's say, but also a broader class of observables across the frequency spectrum. I'll tell you a little bit about what modeling approximations and uncertainties can do to the inference, why you maybe should believe some results and should be wary about extending other results to a broader class. And then at the end, I'll tell you about some of the efforts that I've been involved in to identify robust signatures that are more independent of all of the modeling approximations and gastrophysical uncertainties. I like interactivity, so please interrupt me at any point. Yeah, that's all I have to say about that. Okay, so I probably don't need to motivate the idea that studying black holes is interesting, but just for the record, I will say there's perhaps a conservative estimate of maybe 10 to the 16 black holes in the observable universe. Often, if you look at the centers of galaxies, there's a black hole there, probably almost all the time. Many of these black holes, both at the centers of galaxies and not, launch jets. So these massive fluxes of energy, directed fluxes of energy. These jets are intricately linked to kind of the history of the universe, feedback, how good cookies are here. Also, yes, if you want to get cookies, you can get up at any time. Right, so kind of how galaxies grow, how black holes grow, et cetera. Also, just generally, the environments that we are talking about are quite extreme. So the accretion gets down by the horizon of the black hole to the trans-relativistic plasma. What do I mean by that? I mean that the thermal energy of the plasma is approximately on par with the energy, the rest mass energy of the electrons, the rest mass energy of the composite particles. This is a really rich environment where you can have shocks, which is super interesting, reconnection, so dissipative physics, pair production. So if you're interested in antimatter, we can say there's antimatter. Of course, we have for the galactic center, but also for M87, a really, really rich history of multi-wavelength data. And as you all, I'm sure, are aware, recently there have actually been horizon scale images. So this is really great. We can study these environments from large scales all the way down to small scales, at least at certain frequencies. I guess I have to say this last point, that this is technically, a direct observation of kind of the dynamics of matter and how light moves in the presence of gravity in the strong field regime. Kind of to specialize and give a focus on one of the things that I'm particularly interested in, certainly not the only reason you would care about black holes. I'm going to specialize and talk in particular about the jet that we see in M87, Messier 87. I have been told that if you look in the night sky with a pair of binoculars and you don't live near New York City, like I do, you will actually see a thin little strand if you look in the direction of M87. Certainly, this is what was done the beginning of the, I guess, 20th century, so the 1900s. And so this is a jet. It's coming from some core, and I'm sure you all know this. You can make really simple thermodynamic arguments and estimate how much power should be in this jet. 10 to the 42 to 10 to the 47 ergs, let's say, per second. I like the cutesy number that if you compare this to human scales, the closest human scale is that you take the Earth and turn it into TNT and blow it up 1,000 times a second. So that's the amount of energy that you're getting out of this in principle every single second. And so this, of course, raises the question, how can you produce this much energy, and not just in a single burst, but over a very, very long period of time? Of course, the jet extends thousands of light years. This is also kind of pointed at us. It should be, whatever engine is powering this jet needs to be able to produce large amounts of energies over a very long period of time. The way that we understand how this works is the so-called Blandford-Zonic mechanism, which I will recap for everyone. Basically, the idea here is that in space around the black hole, you have a magnetized plasma. And this magnetized plasma accretes down to the event horizon, accretes down to the black hole. The resistivity is low enough that you have what's called the so-called flux freezing condition. This is Alfvén's theorem. And that is the statement that as you take a parcel of plasma and bring it down to the horizon, what happens is the magnetic flux lines have to be pulled with it, because any movement kind of perpendicular to them would generate infinite eddy currents in the limit of zero resistivity, and that doesn't work. Right, so again, you have this magnetized plasma that's falling down, it's accreting onto the black hole, drags the magnetic field lines with it. The magnetic field lines enter the region of space close to the black hole, where if the black hole is spinning, the field's frame dragging effects, and the field lines end up being wound up with space around the black hole. Of course, as you all know, if you have some collimated magnetic field lines, you have some pointing flux. And so you have some E cross B power that's coming out. We can make this all coordinate invariant if you want, but this is the general heuristic picture of what's going on. This was a theory that was written down in the 70s, 1977 by Roger Blanchard and Roman Zonic. And from this, you can make some general rough estimates of how much energy you would get out of this process. And to within astrophysical precision, this is in fact exactly the amount of energy that, or at least it's consistent with the amount of energy that we measure coming out of M87, for example. Go ahead.
Good question about that. I never understood how they, I mean, it depends on the magnetic field strength, right?
Yeah.
So is it, I sort of how it's imagine it was the other way around. They predict the magnetic field strength by energy estimate. I don't know. I just
no.
really
That's a good point. So in fact, this is your point there, and the kind of order of what you learn from what is exactly Roger Blanchard, whose name is in this, his point about why kind of the classical idea of an accretion disk doesn't work. So he will say, so if you make this inference, you measure the power and you infer the magnetic field, you get that the field should be about a kilogauss. And if you have a kilogauss, then you're in a different regime than accretion, than the standard GRMHD accretion models would predict by a factor of, let's say, 20. There are questions that extend to this. So I don't know how in detail to go right now, but 20 is not that large again in astrophysics. Also, the jet power that you're talking about, that you're making measurement, is really a constraint on the kind of magnetic field here rather than here. And so there are questions. There's also just a broad question of, we see matter from rotation measure. We see that there's accreting stuff at large distance. And so it has to go somewhere. And so anyway, this is, love to discuss it further. The statement about the agreement is more that if you kind of put in if you put in some boundary conditions, some initial conditions for that are consistent again with rotation measures. So from rotation measure, you can get a sense of how much stuff there is, how much plasma from the column depth. And if you kind of evolve that in, then you get something that's within a factor of 20. And as I said earlier, the estimates go from like 10 to the 42 to 10 to the 47 ergs. So that's 5 orders of magnitude difference, ergs per second. That's the jet power.
But you don't pick the initial strength of the magnetic field? That's an output of your simulations?
I see. So there are, yeah, right. So there are different equilibria configuration. So if you assume equipartition or something, which is probably not an unreasonable approximation when you go out to hundreds of parsecs. But yeah, no, absolutely. There are uncertainties. You also have estimates of magnetic field strength just from the brightness temperature, right? So even if you don't know exactly what you're seeing, if you can't resolve the full image, if you look at the source, you see some distribution of brightness temperature. And so from the brightness temperature, along with estimates of what the number density of the plasma is, you can infer some general magnetic configurations. And this is, if you care to read into the details of it, I think it's section 3 of the 5th paper, EHT paper that was published in 2019. So there's this general. Right. Okay.
So
Yeah.
super basic. Assume there are particles in the jet, right? Where do the particles come from? Or do they come from the accretion disk, or are they pair created?
That is slide 30. Short answer is we don't know, and there are good models for each of them. We don't know. Like, most basic question is it pairs, right? Is it electron-positron pairs, or is it ion-electron plasma? And we don't know the answer to that. I think observations in the future will help us constrain this from polarization, but we don't know, and we can generally estimate what the entrainment rate is. So if you assume that the ion-electron plasma has to be coming from the accretion disk, you can estimate how much of that would make it into the jet plasma in general. It's a great question. Okay. Right. So BZ mechanism relies on the idea that there are magnetic field lines that are being wound up by the spin of the black hole. And so if we want to make some inroads into kind of probing this observationally, we need to do 2 things at least. We need to kind of constrain, I said measure, I should have said constrain. Constrain the spin of the black hole and constrain kind of the structure and strength and detail of the magnetic field close to the horizon. So how might we do this? Well, as CK I said, I'm a theoretical and computational astrophysicist. And so one of the ways that I address this question is by running a suite of simulations that include what we think to be a representative set of the physics involved in the evolution of these systems. And you run these simulations of the black hole accretion flow in terms of the fluids, and then you perform ray tracing on it, and you simulate, if this were the initial condition, or if this were the strength of the magnetic field, et cetera, what would you see in the image in terms of the structure of the image, or in terms of the variability in the image? You can also, of course, probe the spectrum. So this is versus frequency, how much energy you're getting. And so in this way, you can say, suppose that you run a whole bunch of different simulations with high spin, and you look at their results, or you look at their simulated observables, and they all share some characteristic features, and maybe you can learn something about that through comparison to observations. So I'm going to briefly go through kind of what goes into each of these 2 steps, the GRMHD simulation and the GR ray tracing. Beginning with the GRMHD, I will remind you, GRMHD is general relativistic magnetohydrodynamics. So GR, because we're near a black hole, M, magneto, because it's magnetized plasma, HD, fluid hydrodynamics. And I kind of talked about two things here. So as inputs, one is the spin of the black hole, which is just the angular momentum of the central object, spin normalized in some way. And then also the magnetic field structure, just to give you a sense of kind of what we mean by the magnetic field structure. You should have in your mind these two limiting cases for the magnetic field structure, the so-called sane and mad cases. And broadly, the way that you should think about these are that, there's some question of, is the magnetic field strong enough to have a noticeable influence on the rate of mass accretion measured in some way? So again, these two regimes are, let's say we measure the inward ram pressure. So you have a fluid, it wants to fall onto the black hole because of gravity. You can measure the inward ram pressure associated with that fluid. But if you put enough magnetic field in the region close to the event horizon, then, as it gets pulled down, as it gets accreted, and because of turbulence, the field will kind of bunch up, so it'll get dense. There will also be kind of these curved structures, and nature doesn't like bend to magnetic field lines. That's an energetically unfavorable scenario. And so if the magnetic field is strong enough, it becomes dynamically important and kind of resists the inward turbulent accretion flow. And so again, that's the difference between these two different regimes. You have sane, standard, and normal evolution, I think acronymed by Ramesh Narayan, and MAD for magnetically arrested disk solution. I don't know who came up with it, but certainly who came up with the acronym, but it's, originally shows up in Sasha Chikowski's papers. Okay, so this is what you should have in mind in terms of the different accretion states, kind of initial conditions to the fluid simulation in terms of the magnetic field. I will, yeah, go ahead.
Does the geometry of the magnetic field that you put in at the beginning matter at all here? Because this is something in with small stellar mass black holes, we often don't really know how to initialize the geometry of the magnetic field. What about in the case?
The short answer is yes, it matters a lot.
So would you literally achieve steady state in one of these two different states depending on the geometry that you're using? Okay.
And in fact, when we run these simulations, that's exactly how we get to one state or another state. We kind of know through heuristics and trial and error that if you start with a vector potential that looks like this, that will end up being conducive toward feeding a bunch of magnetic flux to the horizon. And if you feed a bunch of magnetic flux, you'll build up enough that you go mad. There's an interesting question, right? So the two simulations that are being shown here start with a fluid initial condition motivated by fishbone Moncrief solution, which doesn't really matter. Well, it very much matters, but for what I'm about to say, it doesn't matter. There are other initial conditions. And so if you start with, for example, a so-called chakra body solution, and you use the same magnetic field vector potential prescription, you could have a very different result. So I think in general, there's this question of how you set up your initial condition. And then, recently there's been a lot of work looking at, modeling S2 stars or whatever, modeling stellar winds in the galactic center and looking at what happens there. Of course, there you have some different initial conditions. There are a whole bunch of interesting questions like that. Should the field lines thread the initial disk? So many different questions. Right.
So George, are you planning to talk about resolution as well? I have a question about resolution.
I was not planning on talking about resolution. I'm happy to answer your question. It's also slightly different.
But you think you have the figure here.
Yeah.
So I just wonder how the accretion rate depends on resolution. I guess my guess here is less dependent on resolution for sane because it's turbulent. You assume similar, but for MAD, it probably depends a lot.
Yeah, so one could talk about this for a long time.
We can talk about this later.
I guess a short response to that is that for the sane case, supposing you have enough resolution to resolve the initial buildup of the MRI, which is what's the accretion, I think what you said is more or less true. For this MAD case, you do need to reach some threshold resolution to resolve kind of these thin filamentary structures that I'll show on the next slide. But I don't think that level of resolution is a problem in the current suite of simulations, at least of the canonical initial condition. So if you go to, for example, this chopper body initial condition, just referring to, there it seems, because so chopper body solution is thinner. And so there it seems that you do really need to go to moderately high resolutions. But anyway, okay. So heuristically, how should you think about MAD and sane? So MAD again is this fields are dynamically important. So what are you looking at here? You're just looking at slices of the accretion disk through the midplane. So I have a black hole, it's spinning like this, and I have an accretion disk going around it. We're looking at a slice like this. And these two movies just kind of show pictorially what I was just saying. In the case of the MAD simulation or the MAD accretion state, you have a bunch of concentrated magnetic flux. And it has so much magnetic pressure that it's able to kind of push the accreting matter out of the way. It's able to push the dense plasma out of the way. And so you have these large evacuated regions with very, very low density that just have a lot of magnetic flux in them. This contrasts the sane state where it's certainly turbulent, but you don't have these large evacuated regions. Right.
So on a slice rate going radially outward, it's changing by like order 1, like it's going from like the density is fluctuating by a factor of 10, 1, 0.1.
So I mean, this is
You said evacuated.
4 orders of magnitude.
4 orders of magnitude.
So in the MAD case, you're talking.
Yeah.
I mean, so
Why don't the images change? Oh, because this is midplane and it gets averaged out or something?
No, I mean, they look, I mean, so I guess I don't understand your question. Sorry.
Maybe if you made a cross-sectional plot in the midplane,
Yes, there are evacuated regions where there is no plasma.
so density is gonna be like this and then basically 0 and
If I were
4
to
orders of
integrate
magnitude.
vertically, yes.
Even if, so now if we actually looked at like, these structures extend out of the midplane?
That's right. But even if I were to integrate vertically, you would still see evacuated regions.
I had no idea.
So,
Yeah.
so, here you're showing the spatial variance of
That's right.
the accretion flow. So what if we see the same, like, if we just integrate every bit of the accretion for these 2 different cases and plot a accretion history for the black hole in these 2 cases.
So like if you were, do you mean, when you say integrate, do you mean if you were to compute, for example,
The
the
total
mass
accretion.
flux
Yes.
through the horizon or through
Yeah,
some kind
yeah,
of?
so today you show very different histories in both like temporal domain and or frequency domain.
Yeah, so I don't have a plot of this, but I may have a plot, I don't have a plot of it. So if you were to plot the mass accretion rate for a MAD, for example, versus for a sane, so let's say m dot. Yeah, okay, it's just time. So for a sane, let's say it looks like this. Okay. Just to set some normalization scale. Then for the MAD, you see things that look like this. And so these kind of steep drop-offs exactly correspond to those times when you've built up enough magnetic flux on the horizon, right? So you can't get rid of the magnetic flux. It has to go somewhere. You build it up and you build it up and you build it up, and then it erupts out and bubbles or ejection events. And those, so you see those in the accretion of history. You also see them if you were to just measure magnetic flux on the horizon, which is not the mass accretion rate. It's kind of even sharper there. And then there are some interesting questions certainly about resolution there. So if you're doing ideal simulations, then your resistivity comes from grid scale and so on, blah, blah, blah. So how quickly you can evacuate or how quickly you can erupt this flux, depending on resolution. Yeah.
What was different in the two simulations? What parameters were changed to get one to the other?
So the initial condition starts with the same fluid equilibrium, and then you impose some vector potential on top of it. And so for the MAD, the vector potential falls off more steeply with radius. Okay, cool. So how do you actually perform these simulations? Well, one thing you may want to do is you may want to say, well, let's just take a whole bunch of electrons and ions and maybe positrons and take their distribution function and evolve them all. We understand how that works in principle. We know Maxwell's equations and so on. This is impossible. And the people who try to do it will also tell you it's impossible, and you can tell them that I said that. The basic problem here is that is an incredibly expensive problem because of the separations of relative scales. So for this is, I guess, the M87 accretion system. No, for the Sagittarius star, so for the galactic center accretion system, the system size is something like 10 to the 12 centimeters. So that's the region of space that's in play. The Coulomb mean free path, which we'll come back to, but the kind of distance over which a particle should travel before it interacts with other particles through the Coulomb collisions is 10 to the 17. You'll notice that is larger than 10 to the 12. And then the electron gyro radius is something like 10 to the 4 centimeters. So if you actually wanted to simulate all of these particles whirling around in orbits following these magnetic field lines, you would need to resolve at least 8 orders of magnitude in scale, not just spatially, but also in terms of the time scales, right? So the amount of time it takes for a particle to go around the system is, much longer than the time it takes for, a gyration time. Also, you have to worry about the relevant scales of ions and electrons. There's a mass ratio there of order 2000, as you know. And so you have a whole bunch of different time scales that are involved. You have a whole bunch of different mass scales that are involved. And if you actually wanted to solve for the full trajectories of everything that's going on, this is just incredibly expensive. The nice cute number that Sasha Filipov told me in 2019, so adjusted for 5 years, is that if you wanted to perform a single global simulation of all the particles, what you would have to do is take all of the computational resources that had ever been used up until 2019 and multiply that by a factor of around 2 to the 100. And then you would have one simulation. And so, honestly, maybe that's possible to do at some point, but it's certainly not possible to study in depth. And you'd have to devote a huge amount of resources to performing this one simulation. I would be remiss not to mention, though, that you don't actually have to resolve all these scales. You don't have to do this full problem. You can make approximations and then try and understand what the effect of all these approximations are. And so to this end, I'll just point out, that people have done two-dimensional simulations. They've also kind of changed these mass ratios and made various other approximations for them. Elisa Golishnikova had a, I guess not too recent, but recent in my mind, paper kind of doing a full kinetic simulation. Okay, so these kinetic simulations are great because in principle, you can look at them and look for particular features and then ask, well, from these kinetic simulations, if we make some other approximations that I'll talk about on the next slide, can we still kind of trust the results, or to what extent can we trust the results? How do they compare? The alternative, of course, to simulating every single particle is just to simulate the kind of moments of that full distribution function. This is one of the ways that we conceive of fluid mechanics in general, right? So you have some distribution function of particles, take the moments of it. So how much mass is there total in some region? How much momentum does that have? What's the pressure, et cetera? And then you integrate the Maxwell Vlasov equation, let's say, for how the distribution function evolves, and you get these conservation laws. It's this wonderful, beautiful theory. And then you just simulate this as a fluid. So that's the hydrodynamics, the magnetohydrodynamics. This is what I do. There are a whole bunch of interesting questions about how do you actually close your system, right? So if you have a distribution function of particles, of course, you are losing some information when you take moments of it. And so you have to truncate your moment expansion at some point. And this is actually one of the questions that one should be thinking about when asking how far do we trust EHT results. And I'll get back to that in a second. But this is, again, the picture that you should have in mind. So I run fluid simulations, which are kind of approximations for the full distribution function evolution. Okay, so I talked about kind of this side, GRMHD simulations, fluid simulations. Now I'll briefly talk about what goes into translating those fluid simulations into observables. And here, the name of the game is just ray tracing.
Sorry,
Yeah, go ahead.
it really won't take that long, but I don't see the evacuated regions in your left picture.
So this is the same.
That's Have I just never seen a meridional slice of a atom? I've never seen that. I'm just ignorant. Okay. Do you have one in your talk?
Probably.
Okay.
I certainly have them in backup slides. Often what you see though are averages, azimuthal averages or time averages, and so this may also be influencing, but I mean, right. So the name of the game here for performing this translation from the fluid state, which is a time series of physicist fields, not math fields, is you do ray tracing. So what is the dominant emission mechanism? Well, it's synchrotron radiation, which is just you have particles that are charged. They wind around magnetic field lines, Lorentz law. And so charged particles that are accelerating emit radiation. And of course, since the particles are confined to move in these kind of circular orbits, they emit radiation with particular polarization. And so we can just more or less simulate this to some level by looking at the total number of particles, looking at their temperature, field orientation, and then saying, okay, so we expect this zone of the plasma to produce this radiation with these polarization properties. Then you can track that parcel of radiation out to infinity, out to an observer, accounting for the effects of Faraday rotation, right, and Faraday conversion, which is just that if you have an electromagnetic field that's traveling through a plasma, you know, the orientation of the electromagnetic field and its properties can change with the properties of the plasma. And at the end of the day, you get out images or spectra. So just to kind of train your eye, if you haven't been thinking about this, you have the kind of total intensity, so the total number of photons that you're getting. So that's these guys here, either at fine resolution or blurred to realistic beam that you might get from an EHC observation. But you don't just have the total number of photons, you also have the orientation of the electric field, the orientation and kind of strength of coherent electric field at your observer. So build the little antennas, and you have an antenna that's oriented vertically and horizontally, and you look overall how much energy are they getting, and how much energy are they getting independently in each channel. You have the orientation, and then you can break things up into circular polarization as well. Great. You do this, and as I said, you do this procedure, or I do this procedure to address this problem over a large variety of different initial conditions. And then at the end of the day, you get a whole bunch of movies of the total intensity and also the linear polarization, different points in space. And then you can try and contrast these images with observables that you actually measure to try and learn something. We will very briefly recapitulate what was done in the case of the EHT. So for M87, the name of the game is you look at all these observations, you try and identify robust features across different imaging methods, across different days. And you might say, oh, well, there seems to be a consistent sense of brightness asymmetry. It's brighter on the bottom. There seems to be some coherent, twisty polarization pattern. And these colors, I guess I'll remove that box for a second. These colors are all approximately teal. So they all have approximately the same amount of linear polarization. And I won't belabor this point, but you can then try and understand what this allows you to infer in terms of the physical parameters of the system. So sense of brightness asymmetry allows you to infer the sign of the black hole spin, just because kind of the brightness asymmetry comes from, at least in GRMHD models, comes from beaming effects. And so you can look back and see, okay, why is the plasma moving the way it's moving? Turns out to be because of the sign of the black hole spin. And then this consistent linear polarization fraction, this consistent field structure tells you something about the magnetic fields. This should be unsurprising because, again, we said this polarization comes from the fact that particles are twisting around magnetic field lines. And so you can learn something and say, well, it's more likely that we have dynamically important fields. It's more likely that the accretion system was mad, because if it were not mad, then the magnetic field would be all tangled up. And then if it were all tangled up, why would we see this consistent coherent pattern? You can play the same exact game for the galactic center too. These results were released a few weeks ago. Again, you have coherent rotationally symmetric polarization patterns. You also have, quite strong resolved linear polarization. This is actually, I think, perhaps one of the most exciting at least to me, one of the most exciting results to come out of this recent Galactic Center sort of publications. So strong result linear polarization at levels of 25%. So again, this tells you something about kind of how structured the plasma is and how structured the magnetic fields are in the plasma, peaking at 40%. You look like you're.
Wow, you're really monitoring my facial expressions. I'm flattered.
Everyone, not just you.
I'm flattered. Oh, well, so it seems like in MAD, the magnetic field is more structured, but the plasma is less structured, it has these evacuated. Is
What do
that-
you mean? Yeah, what you've said, that's not the way I would think about it, but quantitatively, what you just said is true.
Is there a reason that's not a good way to think about it, or?
What does structured mean to you? Because I think structured, in terms of the accretion state, I agree with you. But in terms of what you see, right, what you see is only going to come from regions where there's already a plasma. Right, and so if you have these regions with coherent blobs, and so you have some accretion strand here, and then you have an evacuated region, you're only going to see this.
Right.
And so, the fact that there's some other region that you don't see that looks different.
Okay, but within each region, the magnetic field is ordered. So maybe it's a question of scales, okay?
There's a lot of, yeah, good, that's a good way of thinking. There's a lot of power in the low M modes in MADS, whereas and not much power in the high M modes, whereas in SANES, that's not the case. It's kind of flipped. And that's true for the magnetic field structure, but also for the accretion structure. Okay.
I guess that's really clinching the face-on orientation.
Yeah. So it persists up to like 40 degrees. From simulation results, if you go beyond 40 degrees, so 0 looking straight down, if you're beyond 40, it starts to be problematic.
So this emission, synchrotron emission.
Yeah.
Is that typically optically thin or optically thick?
Right. So for these systems, at this frequency, so this is 230 gigahertz, 1.3 millimeter, optical depth is somewhere, let's say between tau is somewhere between 0.1 and 0.5. Good. Cool. Okay. So, what I've just tried to convince you of is that we can actually do something with these data. We can, maybe not learn, the spin of the black hole down to 0.1%, but we can make some inferences. So, what ways do we know that we're wrong? We should always cast suspicious eyes on things. And so one of the ways that I like summarizing that question is to kind of draw out all of the energetics involved in accretion. So here, this is kind of a configuration space thing, black hole, accretion disk, jet, and then this is kind of a more heuristic, what's going on. You have energy reservoirs. And so how does the energy actually flow? So, I'm not going to read this all out, but you have the convection, redistributing energy inside of the accretion flow. Maybe you have Penrose processes that are extracting energy from the black hole, BZ, and so on and so on. Over here, you have, turbulent energy. It can be transformed into magnetic energy, and so on and so on. And so how do we know that in what ways do we know that we're wrong? Well, this is what we don't account for, or we maybe account for in a questionable way. I will say that, this is, I like showing this because it's kind of funny. This is not necessarily a problem. There are good reasons to, put an X over radiation in the case of the Galactic Center. But I will quickly flash just kind of some slides describing how we already know that if we kind of explore these approximations in detail, we can get different results. And so this is just 2 slides. So the first slide is that, extended GRHD and gas kinetics. So as I said earlier, we're truncating that moment expansion. We're not looking at the full distribution function. We're instead looking at fluid dynamics instead of evolving the distribution function. And so what do we miss when we do that? Well, we don't account for viscosity, which is some anisotropic pressure. We don't account for heat conduction, these dissipative processes. And so people are actually looking at how you can add in these dissipative processes into the fluid simulation, and maybe even go to higher order. And what you see is that the properties, for example, of these time series can change, not in drastic ways, and it's worth understanding in detail what that means. These are incredibly expensive simulations to run, but this is a way that we're wrong and that we're trying to understand better. Even beyond the question of are we getting the fluid right, assuming we are getting the fluid right, what if we get the mass ratio wrong? So what if there are 2 nucleons per electron instead of 1 nucleon per electron, if we have helium instead of hydrogen? This is not absurd in the case of the galactic center. There are observations of Wolf-Rayet stars with winds that appear to be 99% or maybe in excess of 99% of helium. And so it's worthwhile to understand that. And you can just do kind of cute heuristics, and you see that polarization properties change, variability properties change, and so on. Just generally going back to the question of these kinetics, if you change the electron distribution function, right? So if you allow your distribution function of particles to be non-thermal, you can get vastly different, for example, spectra, and again, variability properties. You get different properties of flares if you include resistivity. So Bart Ricardo has done a fair amount on this. You get different properties of plasmoid creation, reconnection rates, so on and so on. If you include things like helicity, so if anyone really likes plasma physics and happens to know about conservation of generalized helicity, I would love to talk to you at depth. But it turns out that if you include contributions or constraints on helicity conservation in plasma physics, you can get quite different results in your images and kind of in distribution functions of polarimetric properties. I have to talk a little bit about machine learning. It seems to be something that you have to do. And I'm actually happy to do that in this case because I think this is a really neat result. So of course, in doing these EHT analyses, we generate all of these different simulations. You generate, tens of millions. In this case, I think this number is old. I think it's hundreds of millions now of images. And so this is rife for training some convolutional neural network. And so you take all of these images, maybe with polarimetric quantities involved there, and you can try and ask CNN, in this case, ResNet 18, whether it can predict certain features. So can it predict, given an image, sane versus mad? And the answer to that is yes. Can it predict, given an image, what the spin of the initial simulation is? And the reason that I think this is such a neat result, maybe it's just my ignorance of how wildly successful, machine learning and image classification has been. But right, so what we did for this particular result is we take these tens of millions of images, and these images were generated with one of 5 black hole spins. So negative large, negative intermediate, 0, positive intermediate, and positive large. So plus minus 9375, plus minus 0.5, and 0. Only these 5 spins, and you train a neural network on these tens of millions of images, and then you pass the neural network an image produced with the spin that was not part of the original training set. Of course, you have to do this, otherwise you don't necessarily believe the neural network in the first place. But what turned out to be the case was, right, we passed in some models with 0.25 spin, and the neural network came back and said, well, I don't really know what the spin of this is, but I think it's somewhere between 0 and 0.5. We did the same thing for 0.75, and it said, again, I don't really know what the spin is, but it's somewhere between 0.5 and 0.975. And I think this is super interesting because it means that somehow the neural network has learned that there's some structure in the image that correlates with the spin of the black hole. This is not necessarily surprising, but what it does is it gives us a tool now to go in and try and understand ourselves as humans what the neural network is keying in on. And so the way that you can do this is with what are called feature maps. So you can kind of poke the neural network in certain ways and say, what features are you looking at that most differentiate between different values of spin?
Yeah, so what's the answer?
All right, so it's actually low surface brightness spiral features. So it's pretty much the picture. You had.
Yeah, so I was wondering, like, how many features in such feature maps have you looked at?
That I can remember right now, it was. So sorry, I don't remember the exact number, but
Like
200.
Okay. Like like with human labor or?
Yep.
Oh,
Yep.
How do you get tens of millions of pre-existing black hole images? Is that just a simulation library or something?
Sleekness nets. Actually, honestly, they were quite sleepful because simulations are great. Once you've written the code, you press go and then you go to sleep and the computer's run for you. But yeah, it's just the existing simulation libraries. Yeah, so the answer to this in this particular case happens to be kind of pitch angle versus radius. And so that's interesting. So low intensity spiral features in the disk are what it's keying in on. And so then you can go and ask the question, well, what's actually going on there? Why are they somehow tracing spin? And so I'd happen to have written a paper about this earlier. And this is a really, really rich, interesting topic. In the interest of time, I'm going to kind of skip over it and briefly say, this is another example. So this is a vertically integrated. Well, in some sense, it's vertically integrated. We can talk about video. So, these spiral features come from the fact that blobs of plasma are falling down to the event horizon. And it turns out that they surprisingly seem to be following more or less ballistic trajectories. And so this, of course, is related to spin. There are interesting questions about, is the interface between the magnetically dominated region and the disk at larger radii, is that interface stable or is it unstable, for example, to magnetize galvanic helmets? It's unstable, super neat. Apparently it was not slide 30. I'll just skip that. Right. So can we observe entrainment and can we track jet matter trajectories? That's an interesting question for the future, because if we think that these are somehow related to spin, then we probably want to, in the next set of observations or in the next generation of observations, try and access some of them.
Question on.
Oh, sorry. Yeah, go ahead. CK. CK, your hand is raised. I don't know if you know that your hand is raised, but
Yeah, so I have a question about the spin estimate. Is it possible that it comes from the photon ring offset? So when you train your neural network, did you randomly reposition your image?
that's right. We do randomly reposition the image.
Okay, thanks.
Yep, by both large scale, so just changing the pixel center, but also intra-pixel realignments that we've called jitter. So if you remember the jitter parameter in IPOL, so it's a deterministic rasterized grid for each image. And so in principle, you might have some pixels that you just expect to always be brighter. It's a particular spin. And we got rid of that by jittering the image. But yeah, both large scale translations and intra-pixel jitter.
So this is kind of technical, but like, did you also like rotate your image randomly? Okay.
Okay. So in general, the question of populating the jet, this is a super interesting question that we should address in the future. Again, in the interest of time, I'll go very quickly and just say there are kind of two broad ways that you could get matter into the jet. One is just to entrain matter from the plasma, the ion electron stuff, into the jet because of instabilities or because of shocks and so on. Another one is you could just have direct electron-positron pair creation via gaps or drizzle processes, which is just, you have some radiation field. You know that the background plasma is hot, so it's producing some radiation. And if two photons collide into each other with the right center of momentum energy, they will pair produce via Bright-Wheeler, the Bright-Wheeler process. That turns out to be the one with the highest cross-section for these relevant numbers. And so you can directly compute these rates of pair production, either via drizzle or vacuum decay in general from unscreened electric fields. Broad question, I'm going to skip this because I want to get to the last part of I guess last part of what I think is super interesting about the near future. So stepping back from all of these astrophysical questions, how hot is the plasma? What's the electron distribution? Is there some other way that we can measure properties of the space-time geometry? And so I'm going to go back to this image, M87 image, and just talk about it very briefly. So of course, the first thing we can do if we have computer simulations is we can try and come up with a high resolution facsimile of it. So here, again, we just have a GRMHD simulation that we've ray traced at high resolution. And what may stick out to you is the fact that you have this kind of extended structure, but there also seems to be this ring on top of it. This ring is, of course, a product of lensing, at least in this case. It's the so-called photon ring. And so geometrically, how should you think about this? Well, again, here's that simulated image, and you can decompose the simulated image into a set, an infinite series of sub-images that correspond to photons that made n number of passes through the midplane of the black hole. So think about every single point in the midplane. It doesn't have to be the midplane, of course, but think about, just for simplicity in this talk, think about if you have a whole bunch of emission coming from the midplane, and you have you consider in particular emission coming from this region, you can integrate over all the different locations in the disk. Well, so some of the photons coming from this region will, go up and then they'll go off to a camera. I have a camera way up there. And so you'll see that, but you'll also see some photons from the same location that are shot down and then come up. And so those guys have crossed the midplane, one extra time. And then you have other photons that are shot off at a different trajectory that go up and then come down and then go up again. And those have crossed the midplane of the simulation, or sorry, the midplane of the system yet another time. And so in this way, you can kind of conceptualize every single photon that you receive as an observer as having some tag associated with how many times that photon went around the black hole before it reached you. And of course, this means that if you have some impulsive emission, it will produce echoes, because you have some photons that just directly go to the observer, but the ones that take some time, that orbit around the black hole first, will arrive at a delayed period. And so this is, of course, not a new idea, and it's been worked on, by a variety of people. But the key feature here, or the key thing to realize here, is that I guess two key features are that different paths, in principle, can produce different time delays. Right, so if you have an emission here, it'll have different time delay spectrum than if it were here. And also the path length differences depend on the spin of the black hole. So this is a very kind of idealized case of what these trajectories look like. But in fact, all of the different bound trajectories that you could have around a spinning black hole are quite varied. So you could have some that are in the midplane going in different directions. Those have different path lengths. You could have some that are omitted at some oblique angle to the midplane. These have different path lengths and so on. And so it turns out that if you measure this kind of spectrum of echoes as a function spectrum of echo delay periods as a function of the spin of the black hole, you get different spectra depending on the spin of the black hole. And it's really neat. You can kind of decompose black hole movies into these Green's functions. This is the way I conceive of it. And each echo period, because it corresponds to a different orbital geometry, will arrive at a different location in the image. So if you have a resolved movie of a black hole and you measure these echo delay periods at different points in the image, you'll see, over here, there's very rapid echoing. Down here, there's a very slow echo. In the middle, there's some intermediate echoing. And over here, what I'm going to show you is just a kind of sweep through different spins over here, first through different spins, and then through inclinations and back in spins. And the only thing that you really need to take away from this is that every frame is different. And so if you have infinite resolution, which of course we don't have, and you can somehow measure this echo spectrum, you can uniquely determine exactly the spin of the black hole and the inclination, which is neat. You can, of course, test this quantitatively. And the easiest way to test this quantitatively is with a hotspot model. And so if you just have some really, really simple non-adversarial emission source where you just flash a whole bunch of photons into existence and then they go away after taking their orbits, you can clearly see that spin of 1/4 has a longer echoing period than a high spin case. And if you measure different parts of the image, that's what these different colors are, the echo periods can in principle be different. I like a cute little story about this, which is that when I originally made these plots, I mislabeled one of them. And I was looking at it and I said, this doesn't make any sense. Something must be wrong. And so I will claim that you can indeed tell by eye. You can indeed read the spin from these things. Yeah.
So when we're trying to create these like echo maps.
Yes.
Do you assume a constant accretion rate or you allow it to change?
So it doesn't, so you allow it to change. And these kind of the structure in this is purely from the geometry of the black hole spacetime, right? Because these echo delays are determined by the paths, the geodesic paths. And so as long as the plasma is not massive enough to change the Kerr, to take you away from Kerr, you won't, it doesn't matter in some sense. Now, which echoes you excite will depend on where the emission is. And so it could depend on the emission rate, but the actual structure, like the spectrum, or in terms of where the spectrum could have peaks, doesn't care about that. Doesn't care about the emission source. Yeah.
So what if you have, say, at a certain time, you have a small blob of matter that's accreted, or like glowing.
Yep.
Accidentally, instead of like being the echo, it's kind of faking the echo itself. And how?
Yeah, that's right. So
differentiate?
yeah, that's a great question. The short response is you probably don't want to claim high confidence in a single echo measurement. You want to take some long time series and look for over time what happens. And then that's the just kind of last part of what I was going to say, which is that you don't need to do this with a hotspot model where things are kind of the exact opposite of adversarial, conspiratorial, or whatever. You can just do this with GRMHD. So GRMHD is not necessarily adversarial, but it's certainly much harder than a hotspot model because you kind of don't have control over which parts of the Green's function, what part of the Green's function parameter space you're poking. I will skip to the chase here and say, you can't directly see, right? So in the hotspot case, you could in the total light curve directly see these peaks. You can't see those peaks. Even if you perform an autocorrelation, you can't see those peaks in the GRMHD. And the reason for this is just that the kind of indirect image is much too low flux compared to the direct image. And this just comes from the fact that it takes a lot of fine tuning kind of for photons to go around the hole one extra time compared to, not as many times. And so the way that you actually should perform this measurement is in the visibility domain. So I'm going to take this image, which I'm sorry, it's kind of dim here, but this is just a conventional black hole image. Take the Fourier transform of it. This is the way that VLBI people think about the data anyway. And what I'm going to do is I'm just going to plot a single slice through this visibility space where this slice is at V equals 0. And this is what I get. And now here in this slicing, I again decompose the signal into those different components. So I talked about how, a few slides ago, how you have the direct image, the n equals 0 component, you have the n equals 1, and the total image is the sum. Well, of course, the same is true in the visibility domain. And so here what I've done, as I said, is I've just taken the full image, taking the Fourier transform of it, and plotted out the Fourier transform and tagged each component of power at every single different spatial frequency in the Fourier transform based on whether it corresponds to the direct image or the indirect image and so on. Now what I'm going to do is I'm going to take this thing and I'm going to show you a movie of it over time. So horizontal amplitudes, vertical amplitudes are just take the Fourier transform, took a horizontal slice to it or a vertical slice to it. It's not too important. But what I want you to think about or take away from this animation is that there's a bunch of really interesting correlation structure. So the procedure that I described in terms of the echoes was to take the total light curve and look at the direct image light curve, which is the 0 baseline blue, and then try and look at the delay of the indirect image total light curve, which is the 0 baseline red. And in fact, if we were somehow able to correlate these two guys, so the blue at 0, apparently my x-axis is not labeled, sorry about that. The blue 0 and the red 0, you would see this delay period corresponding, and that was in one of the earlier slides that I went through quickly, but you would see this delay period. But of course, you can't do that in reality. You don't know which photons came from the red curve versus the blue curve. But if you look at this long enough, what you will realize, and we can talk about the math of it at some other time, what you will realize is that look at the red curve out at long baseline. and look at how quickly it's going up and down. And if you just correlate, if you ask, what is the time behavior of the red curve out here compared to the time behavior of the red curve in here, there turns out to be quite a strong correlation. So what we want to do is we want to correlate in time, with time delays, the blue zero baseline with the red zero baseline, but we can't do that. So what if instead we correlate, the total time variability at zero baseline with the total time variability at long baseline? Because this time variability at long baseline is kind of a proxy for what's going on in the time variability at short baseline from the singly indirect image. If you do this, this is what you get. So these are the correlations as a function of delta t at 3 different locations. So I measure the time series of the total light curve, or the total visibility amplitude at zero baseline, and I correlate it with the time series of the total visibility amplitude at 10 gigalambda. I think this is 42 gigalambda, and I think that's 48 gigalambda. These were not too distressingly cherry-picked. So I mean, it works in general, but I don't want to make strong statistical statements here. But the point is that there's a clear difference if you measure, if you compute the correlation between the time series at zero baseline and at, let's say, 42 gigalambda. If you compute that, you see there's this clear peak at exactly where it should be, based on just computing delays in GR. Okay, great. So I think, oh, right. And so this is in principle plausible. So I said 42 gigalambda, that's something like here, which is just beyond geo. Unfortunately, not what Bex is targeting, but for people who know what Bex is. But it's not like you have to go all the way out to Saturn to do this. You could in principle do this with an orbiter that you can see with your eyes. I'm going to skip this, but you can do the same kind of analysis or ask questions in the polarization domain. Bunch of cool stuff there. If you're interested in it, you can talk to me later. With that, I will just conclude and say, black holes are ubiquitous. It's worth understanding. They're cool, but if we care about the history of the universe, it's also probably worth understanding a bit about them. There are promising and exciting results, but there are significant theoretical uncertainties associated with those results. Horizon scale images offer new methods to constrain spin and magnetic field structure, but we should really be thinking also about kind of robust parameter inference techniques. And here's my little pitch for the echoes. And so with that, thank you very much for your attention. Happy to take questions. Also, I went over by 4 minutes, so if you're, feel free to leave. Yeah, go ahead.
My question was just more general about black holes. If
Yeah.
you're like comparing the M87 to the Sagittarius A-star picture, I would expect, because we're like peering into the plane of our own galaxy, that we would see like this crossbar, right? But based on like what like the Einstein like the shadow, right? Like I forget the technical term, but the ring that
The shadow.
yeah, the shadow that's being projected from these geodesics, right? Will you always, assuming like some transparency, like you're peering through like a good chunk of the accretion disk, will you always see a ring?
Assuming that you can always see through the accretion disk and assuming Kerr, so assuming, GR, conventional GR, yes, you always do see a ring. I guess, caveat that with that, like one can envision constructing an adversarial accretion emission structure, right? So if you happen to, if all that all that you're seeing is coming from some like hot blob of gas that's really, really far away from the black hole, you don't see a ring. But so long as you're producing emission kind of near around 3 M, you will, and it's sufficiently spread out, you will, or so you time average, for example, you should see a ring. I don't know if Sam, you want to argue against this.
Well, if it's at John, I don't think you'd see a ring. I mean,
Wait, why not?
you are.
No, but you have, if you have midplane emission, I mean, this is the classic interstellar image. If you have emission in the midplane, you get stuff that's lensed above and lensed below. This is
Some, I mean,
yeah, so there is absolutely a question of how much flux is in the ring, which maybe is what you're saying.
I was gonna say, if you saw the whole accretion disk out to the point, like you're saying, like what's the flux as you get further and further away from the black hole, then sure, yeah, you'd see this crossbar, and then assuming you have like X-ray vision, you see like this warping and then like a ring inside. But because we're kind of peering through all of that and it's like low flux up until a certain point, like right next to the black hole, we'll always see a ring unless there's some crazy accretion happening, right?
Yeah, and I guess I should be sufficiently cautious and say it doesn't have to be crazy emission,
Yeah.
just, you know. Yeah, so it's also, I guess, I am behooved to say, all of the measurements appear to suggest that we're not seeing the galactic center black hole edge on, which is very weird, and I don't understand why that would be the case from a prior's perspective. And there are interesting questions about, you know, whether if the black hole is not spinning, then what does it mean to be seeing it edge on in terms of accretion, disk angular, net angular momentum, and so on. But anyway.
This is, I think, related to what you were just saying, if less so the talk. Do black holes tend to be like aligned with their host galaxies? Is that what you're saying? Why you would expect to see it later on?
I am uncomfortable making a strong claim about alignment of black holes with their host galaxies, so I won't do that. I will say it's weird that the two black holes that we can resolve from Earth with Earth-based telescopes seem to be pointed at us. That just seems unlikely. That was the statement I was making.
Okay.
So there's this really interesting question, kind of going back to the maybe second slide, which is just the formation history of black holes, right? So if you look at recent gravitational wave results, from pulsar timing arrays and so on, there seems to be some weird extra amount. We don't understand the formation history of supermassive black holes in general. How do mergers work? So if you have how do you grow a black hole that large? What are the initial seeds? And if you crash two galaxies together, what is the kind of the time scale on which things on which things should merge, and so on and so on. People in the audience may be much more expert in this than I am. I just think that it's weird that the two black holes that we can see seem to be pointed at us. That's weird. Yeah, go ahead.
Yeah, so you talk about lots of features that we can differentiate between different, say, accretion models in these simulations. So are horizon scale images absolutely needed to tell the difference, or can we get away with some larger scale observable signatures, like maybe spectral energy distribution on a larger spatial scale, or things like that?
Yeah, this is a good question. I think it depends on what kind of statements you want. If you want to make a statement that, this is likely, strong magnetization, you can probably do this with unresolved measurements. There are some really, really interesting questions that you can address with flares, for example, just the time scale or something. So what is the emission mechanism? If you believe general ideas about how you should populate the region of space near black holes, then you can learn, you can look at, for example, circular polarization and say circular polarization, has these features when it's produced by leptons versus not by leptons. And so if we can kind of extract out and look at residuals, we can infer things. I'm not giving you a direct answer to your question. I will just say that, of course, everyone I think would agree with horizon scale data, you learn much more. And then I will make stake my claim in this, which is that I think that it's not just that like, oh, you have more data and so you can learn more things. I think it really does open up a new set of observable to underlying physical mechanism. I don't know, whatever things you could throw there. I think it is fundamentally different and gives you a fundamentally different. I'm also heavily biased, right? This is I have to say that, right? But I also do believe.
So you didn't talk much about radiation transport in these codes. How do you see the future of like your work using radiation transport, and how important is it to the physics that we're doing, especially with EHT?
So by radiation transport, do you mean including the contribution to the stress energy tensor?
Yes.
So you don't mean like producing images or spectra?
Yeah, I mean like real-time radiation calculations.
Yeah,
Yeah.
this guy.
Yeah.
Yeah, so so there's a set of papers going back to maybe 2009, let's say, that will argue, I think correctly, that M87 is kind of just on, right, so we consider the two systems, Sagittarius star, the galactic center, and M87, and these papers will argue that M87 is kind of just on the edge of we start to care about radiative effects. Certainly when the accretion rate is lower than this you don't really care about radiative effects. So, for, in particular, the question you asked, for the two sources that the EHT has published on in great depth at horizon scale, I think there's a good argument that results should be kind of compared against radiation simulations. And there are a whole bunch of different ways to do this. So there's Monte Carlo radiation transport, there's method of characteristics, hybrid with Monte Carlo. These methods, have been tested and are in use. There's also this kind of finite volume radiation thing that was originally written down by Davis and Gami, and now has been implemented in at least two codes, one that I work on a lot. So, I think those are certainly things that should be tested. I think, though, that radiation probably, you don't need to solve the full radiation problem. You don't need to necessarily include it in the stress energy tensor. You can just add in some cooling function, let's say.
Okay.
I think, though, that, if you go to higher luminosity sources, radiation is absolutely crucial for understanding, thin disks, et cetera, where you have photospheres that are far out. And I think that's a super interesting field that I didn't talk about at all.
Okay.
You talked a bit about like limitation and possible missing microphysics of GeoMHD. So I'm curious if like we need to go beyond GeoMHD for like basic variability, or is there any other major issues with our understanding of accretion physics that we need to go beyond the standard IDU?
Yeah, I mean, so I will not talk about this at length, though I could. I think there's, often the story that we really, we're not included, right? So ideal MHD doesn't have dissipation. That's the definition of it. So you don't have, heating increases in entropy, via heating in this way. You do numerically, but in terms of the equation formulation, you don't. And so people will say things like, well, if you include resistivity, you get different spectras of your particles. So you get a different spectrum. You get a different SED, or you get plasmoid production looks different, and plasmoids may be what are producing flares. And we certainly see flares, and we want to understand flares. And I think that's true. However, in terms of the overall energetics of the flow, so in terms of the variability, for example, of the flow in the thermal core at 230 gigahertz, where the EHT is making these measurements, I don't think things like resistivity really matter so much. And in fact, if you look at, for example, the time series in Bart's papers and other people who've begun working on resistive GRMHD, they look pretty similar by most measures. You also, I think, touched on other deviations like viscosity. I don't know where it is. It's probably before this. Yeah. So down here is what happens if you add in a viscosity to your fluid simulations. You can do this, right? All that a viscosity is the pressure anisotropy. You can do that if you have some closure model. You can just say your stress energy tensor has some anisotropic term that looks like one of my hidden slides. Yeah, I don't know if I can make it show that. Nope. Great. Well, great. Right. So pretty much adding in to next order, adding in all these dissipative effects just means making the stress energy tensor T mu nu have a non uniform diagonal component over here in your spatial thing, and maybe allowing these guys to be non-zero. So pressure anisotropy, viscosity, and heat conduction respectively. People have been doing this. It doesn't seem to really address questions of variability. It turns out to be the case. And so if you just look at the results of that, I think it's a step forward. I think it's again beautiful mathematics. You have to, because there are questions about causality and blah 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 blah. It's not clear though that adding in these extensions to the ideal fluid framework will solve any of the outstanding questions. I think we absolutely, again, need to understand how they mess up or how they, introduce scatter into the results, but I don't think they solve any any particular problems.
Follow-up question is like, you mentioned some efforts to try to add in like distributed component from
Yeah.
first principle. Have people used like AHT results to come up some sort of a phenomenological kind of extension of these models?
To directly answer your question, I am not aware of anyone having done that. To opine, I think that would be incredibly hard. And I think that I mean, there are clear ways to kind of improve your formalism, so not from a phenomenological perspective, and you need things to remain causal, for example. So that and it's hard to do that, just writing something down. You need to, right, so there's this whole question of which frame do you solve things in, right, Landau frame or Eckert frame. And so it turns out that when you write all these higher order coefficients, you need to write down something that's causal in two different frames, which introduces relationships between coefficients and so on. And the reason I've said all that is just that solving that is hard enough from first principles. If you try and do some kind of ad hoc thing, you would still want it to satisfy all of those conditions. And it's just totally not obvious to me where you would start. So again, to directly answer your question, I'm not aware of anyone having done that. I also think it's incredibly challenging to do in a way that's numerically stable. I don't know, it'd be interesting, but I just don't know. I'm happy to answer the question. I don't know if.
I was gonna kill it.
Okay, well,
Sure. So, you showed the Green's function movies,
Yes.
context of the light it was. Curious, how would it look like in actual observations? Would you be able to separate it goes so cleanly? As
No.
we saw in the movie?
no, this is kind of a best case scenario, but I think that, you know, just kind of given what I've played around with, I think the signal is there, and I think that, you know, if you know what to look for, so I run simulations, a fluid simulation, and I say, I know exactly what to look for. I see the signal. I don't know. I am not a good enough statistician, nor a good enough observer to understand how all the error budgets and, you know, kind of fold into this. So I don't know how to do that, but I think the signal is there. I think it's worth looking for, but it, you know, it won't look like that.
I think we should speak for another hand.